Okay, let's look at getting rid of heat. Could this be the limiting factor? We know that athletes get extremely hot. Is there some fundamental reason why they can't go any further because they would overheat too much? Well, we know that someone running might burn a few hundred watts, say 200 or 400 watts, depending how fast they're going. Now, some of that energy is actually going into making them move along, but most of it is going into heat. Now, there are always two ways to think about what happens when you inject heat into something, like when you put a kettle on the stove or something like this. Let's plot the temperature against the time. Here's your starting temperature, and now you start adding heat to something, so by putting it on the stove. Now, to begin with, that something, whatever it is, a human running, a pot on the stove, will start heating up. And the rate at which it heats up is given by the heat capacity. So remember, it takes specific heat capacity is the number of joules needed to raise 1 kilogram of a substance by 1 degree. So to begin with, all the heat, let's say when you're running, your 200 watts of heat will go into warming your body up. But then as your body gets warm, there are various ways you can lose heat. You can radiate heat, it can be convected off, you can be losing it by sweat, and all of those get stronger as you get hotter. So eventually, the amount of heat you're losing will balance out with the amount of heat you're generating, the 200 watts, and the temperature will stabilize. So this would be the equilibrium. So normally when doing thermodynamics problems about heat going somewhere, you have to think about these two regimes. Are we in the regime when we're a long way from equilibrium, when the heat in does not balance the heat out? In that case, the imbalance between heat in and heat out will give you the slope of this graph, how rapidly you're heating up. But after a while, you'll normally end up in an equilibrium situation where heat in equals heat out. In that case, you don't need to worry about specific heat capacity. What you need to do is balance the heat in versus the heat out. So which situation are we in for the human body? Let's say you start running or walking up a mountain or something energetic. You're going to be generating, let's say, about 200 watts. How long would it take for that to warm you up to, say, kill you? Well, let's say the human has a mass of about 70 kilos, and we're mostly made of water, which has a specific heat capacity of about 4,200 joules per kilogram. So, factor these in together. It takes roughly 70 times 4,000, which is about 300 kilojoules per Kelvin. So it means to raise your temperature of the body of human by 1 degree centigrade or Kelvin, it's the same in this case, needs about 300 kilojoules. Now, if you remember, walking up Mount Ainslie required about 1,000 kilojoules, most of which ends up as heat. So that should raise the temperature by about 3 degrees. So you might go from 36 degrees in your body to 39 degrees. Whereas an hour's jog might put 2,000 or 3,000 kilojoules up, that might get to 43 degrees. Now, if your human body is raised in temperature to 40 degrees, you are very sick. If it's raised to 43 degrees, you are dead. So what this is telling us is that you can't just store the heat in your body just by getting hotter and hotter. If the heat just builds up in your body, you'd probably be okay for a sprint or something very short. So Usain Bolt probably doesn't need to worry about losing too much heat very temporarily. It only raises the temperature by half a degree or something. But any persistent exercise, like running or climbing or walking a long distance, you're going to have to get rid of the excess heat. So we have to be in the equilibrium regime, not in this regime. This regime before, 20-30 minutes have gone out, you'd be dead from heat exhaustion. So how can we lose heat? And are these methods of getting rid of heat good enough? So I talked about them in turn. There's radiation. There's actually electromagnetic rays coming out from your skin carrying heat away. There's conduction plus wind. The heat is conducted from your skin into the nearby air and then carried away by the wind or by convection in the air. Or there's evaporation when your skin is wet from sweat or by pouring a water bottle over your head, and then that evaporates off. So let's deal with these in turn.